Hello and welcome to EDICON Online. We are pleased to have 3 platinum sponsors for our inaugural event, Samtec, Mini Circuits, and Rohde & Schwarz. Today's keynote session, Democratization of Radar, is presented by Ovi Jacob of VAR and sponsored by Mini Circuits. After the presentation, Ovi will be available for questions, so if you have a question, just type it into the Q&A box on your screen at any time. Now, I will turn this over to our presenter.
Hi, I'm Ovi Jacob, and welcome to the EDICON keynote on the democratization of radar. We're going to present to you today, through both spoken word and as well multimedia, lots of new information about how radar is being democratized. When I say democratization of radar, what I mean is radar is now, for the first time, in the hands of the whole world. For many, many years, radar was something that was in the world of a research lab, in the world of the military and governments. And now, with great advances that we're going to talk about today, we now have an opportunity to see radar in every single walk of life, whether it's in a retail store, whether it's in an automobile, or whether it's even in a smart home. What I'd like to do today is give a little bit of a walk down memory lane, share some history about radar with you, and in addition to that, have an opportunity to introduce to you guys a brand new evaluation kit from VAR and Mini Circuits. This evaluation kit is operating at the millimeter wave level, gives you full control over the signals, and gives you an opportunity to build your own applications. For the first time, we're taking radar from the signals level to the applications level so that you and your colleagues are able to build all types of new applications using radar. So, let's get started. A trip down memory lane. How did we get to where we are today? I could start in the 1880s with Hertz and with Maxwell, but let's move forward a few decades to where things really get hot, in the 1920s. I want to walk you through 3 experiments performed at the U.S. Naval Research Laboratories and talk to you about how some of the concepts that are now everyday to us were first being developed. It's 1922, and we're on the banks of the Potomac River. On the one side of the river, there's a transmitter. On the other side, there's a receiver, what we would today call a bistatic radar. We are transmitting waves from one side of the river to the other, and we're looking at exactly what is being transmitted and what is being received. Lo and behold, unannounced, a ship comes passing by. And when that ship enters into the beam of waves, all of a sudden, the waves that are received fluctuate significantly. Interesting. We have our first bistatic radar. Let's fast forward to 1930. This concept of radar hasn't yet been developed, but things are starting to percolate in different places. Notably, we're staying at the U.S. Naval Research Lab. At that moment in 1930, L.A. Hyland, noted physicist, is scanning the sky, beaming waves. All of a sudden, an aircraft passes through, and again, the wave that's received back on his antenna fluctuates significantly. A second monumental experiment in the world of radar development. Following Hyland's experiments, fast forward one more decade, and we're now at the eve of World War II. World War II saw lots and lots of radar proliferation being used in concert for the first time. In 1939, the battleship USS New York actually has a radar installed, and with a single antenna is both receiving and transmitting waves to be able to understand what else is going on at sea. In fact, one of the large-scale radars off the coast of Hawaii, an SCR-270, actually is able to spot Japanese warplanes approaching Pearl Harbor before that fateful attack. Throughout World War II, radar is a major aspect of the battleground, specifically on the Allied side. The country that actually used them to save the most people was Great Britain. In fact, Great Britain set up the chain home. It was a series of large-scale radars that would be able to provide alerts to tell the direction that the German warplanes were coming on and be able to avoid bombs. These large radar towers send pulses into the sky, up to 100 miles in every direction, in order to be able to detect the oncoming of German fighter planes. The outputs from these systems was a blip on a screen, something you might be familiar with from grainy TV footage. While the war raged in Europe, new radar developments were happening in the United States in parallel. In 1940, MIT set up a new radiation laboratory in which they started to develop the very first microwave radars. These radars were based on the cavity magnetron oscillator developed in the University of Birmingham by a group of British physicists who during the war shared this technology with the US team from MIT. The next big development came with the advent of pulse radars. Taylor, Young, and Highland, names that you're all familiar with, developed these first pulse radars. And now for the first time we're able to determine the height, the range, and the speed of an object with a much greater level of accuracy. By the 1960s, giant, large-scale, electronically steered phased array antennas are all over the sky, tracking airplanes for aviation, and at the very beginnings, starting to understand weather patterns. But the form factor of these radar systems was absolutely enormous. Still, radar was not something that was available to the common person. It was in labs, it was in governments, and certainly in the world of military. With the advent of the digital revolution in the 1970s, things for the first time begin to change. Perhaps the greatest advancement was the ability to do large-scale signal processing and, of course, large-scale data processing. Once processing at high speeds becomes a reality, radar begins to move from the world of academia into the hands of the regular person. Today, RFIC, based on CMOS, has totally revolutionized the RF industry. Companies like Intel, Qualcomm, and Texas Instruments, as well as many research labs, have released at scale, production-level, multi-system integrated transceivers. When we look forward to the next decade and to what we already see available in the everyday walk of life, we can think about where we've come from these large-scale radars, like those deployed by the British Air Force in World War II that were able to save lives, to very small micro radars that can look inside of the skin and be able to detect cancer. Again, radar saving lives. But what I want to really focus on is the ability for radar to be applied to all different types of applications. Not just those life-saving applications, but everyday walks of life. These advances that we've described make radar robust, accessible, and importantly, affordable. It's a total paradigm shift from the world that we came from to the world that we're now going to. Unlike in the past, where the focus of radar had all been on hardware, huge systems to be deployed only in a military context, now we've shifted from the hardware level to the application level. The cost of the hardware has gone down, and the ability to perform complex calculations, to create algorithms, to be able to do complex signal processing has all become more available to the everyman. Obviously, this everyman is an engineer, but the possibilities here are really endless. Through these commercialized radars, we open up this technology to a whole new user base, a user base that's able to create new applications on top of that technology. A parallel would be something like a Raspberry Pi or an Arduino, a low-cost computer processing unit that's enabled many people to create their own simple applications, to be able to create their own simple, small computers, and to be able to understand what's happening inside the box.
Well, there's also another interesting thing that I said the electronics is open source because at the heart of this printer there is something I really attached to, this Arduino board. So the motherboard that sort of powers this printer is a project I've been working on for the past 7 years. It's an open source project. I work with these friends of mine that I have here. So the 5 of us, 2 Americans, 2 Italians, and a Spaniard, we, it's a worldwide project. So we came together in this design institute called the Interaction Design Institute, IVREA, which was teaching interaction design, this idea that you can take design from the simple shape of an object and you can move it forward to design the way you interact with things. Well, when you design an object that's supposed to interact with a human being, if you make a foam model of a mobile phone, it doesn't make any sense. You have to have something that actually interacts with people. So we worked on Arduino and a lot of other projects there to create platforms that would be simple for our students to use, so that our students could just build things that worked.
In Massimo's TED Talk, he describes how the Arduino open sources the concept of imagination. I believe with radar, we're about to come to a generation very similar. In that spirit, we're excited to introduce to you the VTrig. VTrig is a high-frequency evaluation kit. Let's take a look. All of the activity is powered by Vayar's chip. This is an RF imaging ASIC, approximately 2 by 2 centimeters, which is made out of silicon. You have here in the same system 40 antenna, 20 TX, 20 RX. This transceiver system is able to drive applications that are ultimately endless. You as the user have full control over a frequency range of 59 to 67 gigahertz. You have control over the resolution bandwidth and as well which specific range you want to scan at. In addition to that, we have multiple profiles for the antennas themselves. Whether you want to have a step function that includes all 20 by 20 or you want to have fewer antennas with a different purpose. As noted, the VTrig connects to your processing unit via USB. Your outputs will be the raw data, the INQ. You can take this data and build applications on top of it, driving your own algorithms to achieve whatever results you want to have. Let's go to the lab to see the VTrig in action. Welcome to Vayar's RF laboratory. We have here today a VTrig demo set up to show you how the system works. The VTrig here is a radar and it's generating signals as we speak. Look at the screen. You see the signals being generated by the multiple antenna pairs. I'm going to wave my hand over the unit and you'll see the change on the screen. Did you notice how the waves being generated changed? What's happening here is that I've introduced a new reflector, my hand, into the arena. When the radar waves hit my hand, those waves that are received back, similar to those experiments we saw previously, have fluctuated. There's a different wave that's being received, and the signal changes. With the VTrig, radar is really in the palm of your hands. I want to walk you through a couple of examples of applications that we've built, applications that are available to anyone who has this technology. Let's start off with perhaps the most simple, people tracking. Generally, when you want to track people in a room, whether it's in a home or whether it's in a retail context or anywhere, the way you would track them is you would take a camera and the camera would see a person and you'd have some type of complex image recognition software that would be able to determine that is a person, that is a man, that is a woman, a child. We can do the same thing with the radar. What happens is we create an arena in the room. We're using the 3 Cartesian coordinates, an X, a Y, and a Z, emanating from the antennas of the VTrig. We create this arena, and inside of the arena, the VTrig transmits and receives radio waves. Everything in the room that has a reflection will be able to bounce a wave back to the VTrig. The receivers on the VTrig will then collect that information, and at this point, we're able to place an algorithm that you can create on top of those signals, on top of that raw data, to be able to determine what it is that the sensor is seeing. Is it a person? Is it a chair? Is it a dog? Depending on how much resolution you have, you can get better, higher definition images. And when I say images here, I don't mean pictures, I mean radar images. We've been able to create systems whereby those radar images with our algorithms are able to be interpreted as not just object recognition, but actually to do classification, to determine that's a person, he's standing up, he's sitting down, that's a dog, it's running across the room, so on and so forth. Here's another cool application we've built with our VTrig. We're able to create a point cloud of those images. What I want to do now is I want to show you a point cloud that we've applied to an automobile. The sensor then tracks the environment and creates a point cloud of the driver. Take a look at this short video that we've created that shows the VTrig in action. With the VTrig, you're able to actually determine how many points you might have in your point cloud, depending on how many antennas you utilize, which profile, and also depending on how many data points you collect based on your resolution bandwidth and the frequency range you choose to employ. In addition to that, here's another cool application. We can use the same thing to be able to create images in the near field. Here's one example. We're going to now look at the inventory on a shelf. We've noted how much resolution you have with the V-Trig based on the ability to create many, many, many data points. We can use the same type of concept to be able to determine the breathing rate of a human being. Perhaps somebody might be sleeping on a bed, and you want to be able to track the effectiveness of their breathing while they sleep to be able to determine whether they have sleep apnea or whether they're sleeping well. Here's another example of the V-Trig in action. Before I leave you, I want to go back to the automobile, where we're seeing many radar applications come to life. Here's another concept we've used the V-Trig for. You might want to use this in any context, but let's look at it here in the context of an automobile. When we think about collision avoidance, we have to be able to not just determine that there is an object somewhere out there, the same way the British military did in World War II, but here with a much smaller form factor, operating at much faster speeds. Here, we're able to determine collision avoidance for a car. I want to close with one more application that brings us right back to where we started. When we began, we talked about radar being used in a military context, in a research lab context, always with the purpose of saving lives, whether it's to detect enemy fire or whether it's in a smart home with a very small form factor to detect a fall. How many of you have an elderly grandmother or an elderly parent who lives by themselves? They want to continue living with dignity. There's no way you can put a camera in a bedroom or a bathroom, but with radar, in a private and dignified manner, and as well one that's affordable, you're able to determine the posture of your parent. In fact, not only can you detect the fall, but you can create an entire suite of applications for health and wellness. So that's the V-Trig. Lots of opportunity, but really, we're at the beginning of the road. As radar continues to be more and more democratized, companies like Vayar will continue to put radar into the hands of users, put complex technology in a simple manner to enable people to use it and build incredible things. We've seen applications of the V-Trig, and we've discussed some of the earliest applications of radar. Remember when we were sitting at the banks of the Potomac River, a transmitter on one side and a receiver on the other. When a boat passes through, whether you know it's coming or whether you don't, it creates a fluctuation. I believe we're at a point now in the landscape of radar, in the context of technology, at an arc, at a moment in which radar is going to take off. 5, 10 years from now, who knows? You'll see radars in your everyday walks of life. Similar to how you've seen it getting started this past decade, there's only one way to go.
Thank you, Ovi, for that interesting keynote talk. We have time for a few questions, so if you have anything that you would like to ask and you're attending live, please type it into the QA box on your screen. So first question for you, Ovi. You mentioned radar being used in the smart home. How exactly is radar being applied in homes these days?
Thanks for the question, Janine. Radar is being applied in homes in a number of different ways. I can mention a couple that Vayar is working on and a few others that we've seen in the market. One aspect is what you would call elderly care. So we do quite a bit when it comes to not just fall detection, which has become quite a big application when, for using radar, but also we do quite a bit when it comes to monitoring wellness. So, for example, you would never want to have a camera inside of a bedroom or a bathroom, but you certainly would want to have a scenario whereby you could track somebody's activity level, whereby you could ensure that your elderly mother who's living in a different state is getting out of bed in the morning, and things that are even more mundane, like, how to get, how many times a day does he or she use the restroom. So certainly in elderly care where privacy is primary, we see quite a bit of radar applications coming to the market. Another area, I think, where it's become quite prevalent, again, a lot of it because of privacy, but also because of the cost advantages, is for automation. So we've talked to a couple of hotel companies, and I've seen quite a bit from some of the competitive chips that actually are using radar for automation. So, for example, when somebody leaves the hotel room, the air conditioning unit might not go off, but utilizing some type of radar, which can give you more information than passive infrared, and obviously would be much more private than a camera, you can actually create quite a bit of automation, whether it comes to something simple like lights or HVAC, all different types of applications related to automation and energy efficiency and saving. So those are two areas in which we see a lot of movement for radar in the smart home. Obviously, there are others. I could think of one more simple example, just where to send a Wi-Fi signal based on occupancy, where somebody is sitting in the room to have a stronger Wi-Fi signal. So those are some examples that come to the top of my head, but I think what's nifty about these evaluation kits, not just from VIAR, but also from other companies, is that folks can actually build their own applications. So if there's a way that you think could improve, how a house runs, or could bring some other type of benefit, then certainly I think it would be valuable to pursue that.
Okay, great. On the topic of applications, we have another question on what medical applications have you seen?
Okay, so when it comes to medical applications, I had mentioned some of the things that we're doing in the world of healthcare. At least our company, VIAR, we tend to separate between what we would call, like, let's say, medical devices versus healthcare applications. When it comes to medical devices, I think it's pretty well known. Our company, VIAR, was started based on some academic research related to looking inside of the skin and using very low frequencies to be able to penetrate the skin and to be able to do research around detecting cancer. We've started off with a medical device that's under development for detection of cancer inside of the breast. But I know that there are quite a few other, universities who are not just looking at detecting cancer or detecting other types of changes in the body inside of the breast, but in other parts of the body. Depending on where you want to go, if you want to penetrate into the skin, there are lots and lots of challenges with radar. But certainly that's one area where we see quite a bit of work on the medical side. When it comes to healthcare or home care, for example, there we see very, very different types of applications. I can give you one example that was alluded to in the presentation with the segment on breathing. We're doing quite a bit of custom work for companies related to sleep apnea. So that's an area where it certainly relates to medical devices using radar, but it's not directly, it's an area where we're using radar to be able to detect sleep patterns based on breathing, based on some other factors, like, for example, the movement of the body when somebody sleeps. There's quite a bit of work there around sleep and research around sleep, and obviously, like I just mentioned, for health and wellness. I think that's where I would say the biggest action in the world of radar when it comes to medical. I would break it up into those two categories, and just to echo that point again, I would say there certainly is quite a bit being done in medical devices. I'm mentioning looking inside of the body, but there are other aspects of medical, of radar being used in medical devices. And secondly, on like kind of the healthcare and wellness, where you're using radar, not necessarily radar imaging in the same way, but radar monitoring in a slightly different way to be able to, to apply to healthcare scenarios.
Okay, great. We have several I think they're going to be quick technical questions for you. The first one is, does the VTRIG 74 use FMCW radar?
Yes, it does use FMCW radar. That's correct.
Okay. The next technical question is there a processor on your board?
Could you repeat that?
Sure. Is there a processor on the board?
Okay, excellent question. So let me maybe take a step back on the processor question. For the VTRIG, you will need to connect to an external processor. The actual propagation of the waves and the driving the transceiver system will have to work in tandem with a separate processor. I can use this as an opportunity to talk about the chip for a minute. The VTRIG is an evaluation kit and gives you a chance to evaluate the millimeter wave system. The chip itself does have DSP on chip at a certain quite a strong DSP on the chip itself. For this version of the VTRIG, it's not available for use. I could tell you the history of it. We released this chip a little bit under a year ago to the market, and we first released it from the standpoint of doing millimeter wave applications. In tandem with that, we built the DSP into the chip, and we're just starting to build out an API for the DSP as well. So it's possible that at some point in the future, folks will be able to utilize the DSP on chip for this specific board. But at this point, you still have to use an external processor. It's a great question though, because it really alludes to some of the things that we're capable of doing. So, for example, if you think about radar in a retail context, one of the big advantages you would have from a radar over, let's say, any type of optical sensor or camera is that you have to have an edge processor on site that can do some of the heavier, let's say computer vision processing, or those algorithms to interpret what the camera sees. So for our situation, when we would go to commercialization, let's say we would have customer that would want to commercialize one of our systems in a retail context, we can actually utilize the DSP on chip. So it's a major advantage, and this is not just something associated with VIAR, but the fact that that the signal processing can be done in an efficient manner is really quite impressive, and really distinguishes radar from other technologies. So it's a great question. Unfortunately, at this stage with the VTRIG, you do have to use an external processor, but I anticipate that in the future you'll be able to utilize a DSP.
Okay, thank you. Another question is, what power levels are used in the VTRIG?
I have a data sheet that I can send you. I don't recall the exact, but if you just get me the name of whoever it is that asked that question, I can send him the data sheet and have the power levels that we're using in the VTRIG. I don't want to speak in front of a room full of people without knowing the exact amount, but I can definitely send a data sheet and let you know. It's not heavy power.
It's funny. It's almost like there was a setup there, because another question just came in and said, is there a publicly available data sheet?
Yeah, so there is a publicly available data sheet, and you can get it on the Talk Sponsors website, actually, on the Mini Circuits website. If you can either search VTRIG Mini Circuits, or you can search Mini Circuits Evaluation Kit, and you will pop right up to the you'll have not just a data sheet, but we'll also have some videos there and lots of other information. You can actually order a VTRIG from there as well. Mini Circuits is an incredible partner, really, one of the, if not the leading company in the world of radar and in the world of RF components. So we're really proud to be able to partner with them on this. And we don't just offer the board and the software, but also obviously the support that's necessary to get it up and running and to build drone applications. So just go to the Mini Circuits website and you'll see it right there.
Okay, so a follow-up question, is there a data sheet for just the chip?
I can, again, I don't know who's asking the question, but I can provide a data sheet for the chip itself.
Okay,
I have both a short one, a long one. Whoever it is, just please send them my way, and I'm happy to talk with them about getting a data sheet for the chip. It's if you want just a little more information on the chip, it's a 65 nanometer RFIC, and it has the ability to transmit and receive waves at 3 different frequency bands, both low frequencies, 24 gigahertz, and as well from 57 to 71 gigahertz on the chip level. So it's quite a robust chip, and there's quite a bit to do with it. It has 72 transceivers and is quite a powerful chip. So I'm happy to share more information on the chip as well.
Okay, fantastic. So that's pretty much all the time we have. So thanks very much, Ovi, as well as our sponsors, especially Mini Circuits, who sponsored this keynote. Thank you, everyone, for joining us for this special EDICON online event. Thank you.
All right, thanks very much. Bye.